Welcome to the first bonus episode of the New Quantum Era podcast. The show will be sticking to its regular weekly schedule, new episodes every Monday, but every now and then something happens that's timely enough that I want to get it to you right away, and this is one of those times. Iceberg Quantum from Australia made a big splash last week with the announcement of their Pinnacle architecture and the results they got with it. Namely, a dramatic reduction in the number of physical qubits required to crack RSA 2048 using Shor's algorithm. Now, this is a theoretical result. Nobody's about to break RSA today or anytime soon, but it's still really newsworthy. Originally, resource estimates for factoring RSA 2048 on a quantum computer were around 20 million physical qubits. Then last year, Craig Gidney of Google published a paper that brought that number down to about 1 million. And now Iceberg is claiming fewer than 100,000. Gidney's paper made a huge splash with a 20-fold increase in efficiency, and what we're talking about here is an order of magnitude more efficient than that result. That is a massive leap. Of course, there's a reason this particular benchmark captures people's imaginations. Shor's algorithm is one of those things that first put quantum computing on the map. It makes quantum computing tangible. You don't have to explain what a Hamiltonian is or why simulating subatomic particles is going to matter. Everyone understands encryption, and everyone understands what it would mean to break it. In fact, there's a great piece of history here. When Peter Shor first presented his factoring algorithm at a seminar, he was introduced by Len Edelman. Len Edelman, the A in RSA, one of the inventors of the very encryption scheme that Shor's algorithm threatens. And for movie buffs out there, Edelman had also served as a mathematics advisor on a film released just 3 years earlier, Sneakers, starring Robert Redford, about a team that gets hold of a device that can crack any code. So in a way, this is an example of life imitating art. Before we get into it, a quick word from today's sponsor. This episode is brought to you by Qubits OK, a dedicated job board and research digest for quantum computing. If you're building a career in quantum or hiring for one, this is the signal in the noise. Every week, they send out curated job alerts filtered by over 400 specialized quantum tags, trapped ions, QEC, quantum ML, all of it. And they run a daily archive digest that surfaces the papers that actually matter to your specific research interests. This is actually how I found Qubits OK. Initially, I've been trying all the various ways to make sense of the enormous volume on QuantPH. And Qubits OK really does that for me. And I go there on a daily basis. And that's what makes them really powerful as a job listing site. It's free to subscribe. Head to qubitsok.com and sign in in like 30 seconds. It's free to subscribe. Head to qubitsok.com and sign up in 30 seconds. And if you're hiring in quantum, use the code NewQuantumEra-50 for 50% off your first job posting. That's qubitsok.com, code NewQuantumEra-50. The link is in the notes. So today's conversation. I'm joined by Larry Cohen and Paul Webster from Iceberg Quantum. Larry is the co-founder and chief science officer. Paul is their quantum architect. Both did their PhDs at the University of Sydney under Stephen Bartlett, one of the world's leading researchers in quantum error correction. They've spun out of that group to build what they call the arm of quantum computing, a company that aims to design fault-tolerant architectures for any hardware platform. You'll hear about the Pinnacle architecture, how quantum LDPC codes beat the standard surface code approach in efficiency, what the RSA result really means and what it doesn't, and where they think this is all headed. Let's get into it. Thank you very much for joining me on the podcast today. I saw the paper that you posted to the archive last week sometime and immediately knew I wanted to have you on and shot an email over to Paul, and you very graciously responded quickly and agreed to be on the podcast. So it's very timely. It feels like I'm almost breaking news by having you guys on. The paper was about using QLDPC error correction and an optimization of Shor's algorithm based, I think, on some prior optimization work to get the resource estimation for breaking RSA 2048 down to about 100,000 physical qubits, which is an order of magnitude smaller than the prior resource estimations. So that's what caught my eye, and I think everybody else's. So welcome to the show. And do you want to start just by quickly introducing yourself? We'll go with Larry first.
Yeah, first of all, thanks for inviting us. It's great to be here. So I'm Larry. I'm one of the co-founders and also the chief science officer at Iceberg, and we're a company really just dedicated to developing fault-tolerant architectures for quantum computers, and in particular, developing fault-tolerant architectures with improved, physical overheads, when compared to what people kind of expected you'd be able to do a few years ago. That's really kind of our mission, is just to bring down the number of qubits you need to, do useful quantum computing.
Excellent. And Paul?
Yeah, my name is Paul. So I was just excited by the vision, I guess, that Larry and his co-founder, Sam and Felix, have about Iceberg Quantum. They hired me about a year ago. So now the architecture lead. So in that role, I was overseeing a lot of trying to put their vision into practice to try and actually realize the things that we hope we can do.
Awesome. Okay, great. So, I guess there's a ton of stuff to unpack about this paper and about Iceberg itself, and the pinnacle sort of almost system architecture that you're working on, in a sense. I guess the starting point is, QLDPC is relatively new in the topic of quantum error correction. I think we're more familiar with hearing surface code. That's what Google's Willow demonstration was implementing. What is QLDPC, and why did you sort of select to work on that error correction method?
Yeah, so maybe a bit of, I guess, background obviously is that quantum computers need error correction and fault tolerance to be able to operate, because the qubits and the hardware and the gates, they were all so noisy, and so you need to do something. And so for a long time, people were very focused on something like the surface code, and the appeal of the surface code is that it has this nearest neighbor connectivity, right? So you can lay out your qubits on a chip, and they only need to talk to the other qubits that are right next to them. And obviously that is quite appealing, especially if you're building certain kinds of hardware like superconducting qubits. So I guess QLDPC tries to kind of change that up a bit by saying, well, assume you can build hardware that isn't required to just be able to, where the qubits don't just need to talk to the qubits that are right next to each other. What can you do with that, for example? And it turns out you can do quite a lot. And so in particular, like even on a quite theoretical level, we know that there are these bounds to how densely you can pack information when everything needs to be local, right? So with just the surface code, there's this just inherent kind of overhead. You need a certain number of physical qubits to be able to get a certain number of logical qubits out. And so with quantum LDPC code, that's kind of no longer the case. And so now you can imagine having like an error correcting code block, which can encode like multiple logical qubits. And potentially like a lot more than you can in the surface code. And obviously that's very appealing because, now you can do useful quantum computing with far fewer physical qubits.
So just to interject for a second, so the physical constraint of the next neighbor connectivity in superconductor, that's sort of the lattice, the sort of almost naive approach to laying out qubits in a square grid, and you've got sort of we've all seen the picture of surface code being drawn out as a diagram that almost exactly mirrors the topology of the qubits on the physical chip. So what you're saying is that if you sort of throw out that nearest neighbor connectivity as an assumption, and you assume that you can connect to qubits that are physically further away in the system architecture, that opens the door to different mathematical approaches to error correction. Is that accurate?
Yeah, that's exactly right. And in particular now, people have this picture in their mind exactly like that of people laying out qubits on a chip. But now we have all these different kind of hardware platforms that that are kind of becoming quite prominent, like neutral atoms, like trapped ions, like spin qubits, like photonics. And they just don't have these same constraints, right? With trapped ions and spin and neutral atoms, you can shuttle them around. With photonics, you can move things kind of wherever you want, using optical cables. And so, there's this whole plethora of different hardware platforms now that just don't have these constraints. And yeah, it's why it's such an exciting time to work on these kind of fault-tolerant architectures that don't assume this anymore, so that you can really find out, what can we actually do? How far can we go in terms of bringing down the numbers?
Right. So it's potentially more efficient in terms of, physical qubits to logical qubit ratio. And LDPC itself is a classical error correction approach that I think it dates from the early 60s, if I'm not mistaken. When and where, who sort of had the insight that it could be adapted to add a Q in front of it, which sounds like sort of the the stereotypical thing with any technology. Just put a Q in it, now it's quantum, right? But it seems to be working here.
I think people started thinking about this a while ago, actually. Maybe the first paper in this came out 20 years ago. It's a very natural thing. In some ways, it's more of a natural thing to think about in quantum coding than it is in classical coding. And the reason for that is because, so what is LDPC? It stands for low density parity check. But essentially what that means is maybe qubits need to be able to talk to each other non-locally, but they don't need to be able to talk to a lot of other qubits. Each qubit only needs to be able to be connected to a few other qubits. And obviously, when you're trying to build quantum hardware, that is actually immensely useful. Even if the non-locality is a bit trickier, the fact that it only needs to be able to talk to a few is, for actually a whole variety of reasons, very useful. And so it's actually a supernatural thing to think about in quantum computing. So people have been thinking about it for a while, but mostly from a very theoretical kind of standpoint, and less so from a practical, how do we actually implement this standpoint.
And when you say non-local connectivity, you mean that just in sort of a physical distance way, not a quantum entanglement way. Is that right?
Yeah, if you wanted to lay it out in 2D, you wouldn't be able to do it in a local way.
Right. And in fact, I think that's why IBM's approach is a biplanar chip, right? They've got two planes to the chip so they can actually have these longer distant connections in addition to the nearest neighbor, the qubits that are much closer. So my impression of QLDPC initially was that it had a lot of promise for sort of longer term storage of quantum memories kind of scenarios, but there were some hurdles for performing logical operations. Is that right?
Yeah, so this is actually exactly this thing that I worked on during my PhD and kind of why we started this company. So
I knew it was a smart question.
Yeah. During my PhD, I exactly worked on this problem of how do you actually do logic in quantum LDPC code and not just how do you use them as a memory. And that, I think, really kind of, for me at least, kind of, started kind of this whole journey. And then there's been a lot of great work since on that same problem, and a lot of great work on the hardware side as well. And so it's all kind of converged to start to make quantum LDPC codes a really viable solution, not just for memory in a quantum computer, but really for doing everything essentially.
Right. And so your approach, you're doing some form of magic state distillation or something. Is that correct? I was reading through, you were talking about the blocks being able to do almost being a magic state engine, it sounded like. Is that right?
Paul, maybe you want to...
Yeah. So there are a couple of different things happening there. So the magic engines are sort of a different part of it from the main solution that Larry was talking about, that he made in his work. So Larry's approach is really what's called generalized ladder surgery, or just generalized surgery, which is really a way to take a code and append some extra system to the code that allows you to do certain quantum measurements that have the effect equivalent to performing quantum gates, the kinds of unitary operations that you'd usually do. So in that sense, it has, I guess, in common with magic state injection and those kinds of methods. It's the idea that you're adding another system in to solve a problem. But it's quite different in that it's not dependent on this idea of necessarily preparing a state that you can inject into the system. Instead, it's really about just allowing yourself to do certain measurements that reproduce the effects that you would get from directly doing the gates.
Oh, cool.
It's a generalization of the standard method used in surface codes, which is called ladder surgery, where the original term comes from. In that case, you're really talking about having different patches of surface codes, and you merge and split them, and different ways of merging and splitting them allows you to do different, again, measurements that are equivalent to different gates. This is a generalization of that, where instead of just merging or splitting two different systems, you've really prepared a different kind of system that can merge and split in different ways to your code in order to do these different measurements. Whereas the magic engine is a different aspect of that, which is really about adding in some extra ingredient there that allows you to do the kinds of gates, what we call non-Clifford gates, that you can't do with the generalized surgery. And that too is the surface code methods, where they do a simple approach.
Yeah, I mean, that's kind of the challenge with either the QEra approach or the IBM approach, is that the QLDPC code is protecting Clifford operations, but not Pauli operations. Is that right? And they have to sort of perform that magic state distillation or the lattice surgery to get those Pauli operators. Is that?
So it's not quite the Pauli operators in some sense are the most basic level. So we're able to do them in either the surface code or the LDPC code. The next level up is what's called these Clifford operations. And those are the kinds of gates that until Larry's work in the last few years, it wasn't very obvious how to do them. Those in a sense were the roadblock. People weren't sure the best way to do these Clifford operations in LDPC codes. The next level up, what you need to add the Clifford operations to be able to do a universal quantum computation. So all of the gates that you would need to do to actually do a quantum algorithm instead of something that could be done on a classical computer. Those are what we call, not very imaginatively, non-Clifford operations. Those are what we get from injecting the magic states. So the magic engine idea that we have in the paper, that's a relatively straightforward generalization of the approaches that people do in surface codes, where they talk about having magic state factories. You produce a magic state and you inject a magic state in, and that state that you inject in is it's a resource, it's a tool where once you have this state, that allows you to do non-Clifford gates when you couldn't before. The magic engine is a way to really make that process work in LDPC codes. So it's just a way to kind of really to lubricate that process to make sure that we've got this constant input of non-Clifford gates in this more complicated setting where we don't have lots of surface code patches that we're merging and splitting in the way that people have in the past.
Interesting. And so, I mean, returning to the paper, there's obvious reasons why Shor's is used as a benchmark. It's well understood. It's the first sort of, it's the thing that kicked off in many ways the serious interest in quantum computing. It's easily translatable across other technical domains, even business domains. The idea of breaking encryption features in, motion pictures like sneakers, for example. Everybody knows it. But I mean, in a sense, you're still talking about 100,000 physical qubits. That's still quite a distance away in terms of engineering and shipping devices. What's the input? Like, how does this paper and this work relate to what Iceberg is trying to do as a startup? Essentially, what's the business strategy you're actually pursuing?
Yeah, I mean, on a technical level, we started to develop these kind of fault-tolerant architectures, and obviously, the reason for that is that we think that by really having a company that's just kind of focused on doing this kind of work, we can really kind of push the boundary of what's possible here, right? And so this is kind of the first example of that. I guess for a while now, people in the field have thought, we could use quantum LDPC codes to bring down the overheads, but no one had properly crunched the numbers in a proper kind of quite rigorous resource estimate. And I think this is kind of, one of the first kind of big attempts to do that. But it certainly won't be the last. And so, I don't think, this is not the end of the story. There'll be more improvements. And so, as a company, our position is that, we think this is an immensely valuable, fundamentally valuable thing to do, right? When you think about the things that go into building a quantum computer, we need to, obviously, hardware people will keep on improving the hardware, and people like us and companies like Iceberg will kind of bring down the numbers that you need to do kind of these useful algorithms, things like RSA or like material science simulations, quantum chemistry simulations.
Right.
And
You had
when
Hartree
these,
Fock in there as well. So yeah.
yeah, and when the Fermi Hubbard stuff, and so when these things kind of
Fermi Hubbard, that's right,
converge and meet, we'll be able to do something useful. And so we work with like various hardware companies to kind of see these kind of architectures implemented on this hardware. So we like work with trapped ions and photonics and spin qubits at the moment, to see how architectures like Pinnacle and other kind of work we're doing will impact their timeline and eventually to see this kind of realized on some actual quantum hardware.
Yeah. I noticed that you on your website you list a variety of hardware partners. So there's and I think you call it in the paper hardware agnostic in your approach. So in a way, this is sort of advancing the theory into a workable model that can be potentially implemented on multiple hardware modalities. Which I mean, that's obviously really, really valuable. Do you see yourselves as almost, a consulting firm providing that expertise, or are you trying to productize this in some sort of like a, firmware components that could be licensed by hardware vendors?
Yeah, I think much more the latter than the former. I think especially, if you look at something like the classical space, some of the most valuable companies today in the classical space are not the ones that actually fab the chips, right? They're the ones that kind of operate at this more design level, right? So companies like NVIDIA or ARM, they don't fab things themselves. They just kind of design the chip and let other people actually make them. And I guess, our belief is that, it's going to be quite similar in quantum computing, is that one of the big quantum computing companies will be a company that operates at this layer of like designing the architecture, and then works in conjunction with, the people that build the hardware to actually build the quantum computer, right? And I guess in terms of, like the business model and how you make money, there are lots of particular ways that can go. And you see that even in the classical space, some companies license out their products. But, I think the core belief is that there is like a lot of value just at this level of designing the architecture.
Yeah.
And so that's really where we want to operate.
Would it be safe to say, I mean, error correction is where you're starting, but to be an NVIDIA or an ARM in quantum, you'll have to have full sort of system architectures, at least at a component level that you can customize and use for, the Apples or the the Intels or the AMDs of the world, right?
Yeah. And I mean, there's also like a whole software ecosystem you can build around this stuff, right? Like even just on the error correction side, there's like decoding and actually how you do that and how you implement that. And there's all the software to actually like orchestrate the architecture and actually like on runtime know what to do, the software to like compile down the algorithm. I mean, there's a whole bunch of things that you can kind of build around this core kind of product, right? So it's pretty, I think, limitless what we can do.
Yeah, and in the paper you did call out that readout is sort of an open problem still, right? I mean, it's very computationally challenging because of the nature of the architect. The QLDPC algorithm has a lot of computational challenges for syndrome detection. Is that right? Paul, is that something you're tackling?
Yeah, definitely. So I think definitely this problem of what we call decoding, which is really exactly you do some measurements, you find out what we call an error syndrome, which tells you about information about what kind of errors might have happened in the system. And then we run this classical algorithm called the decoding algorithm that tells you, okay, given what we found out about the error syndrome, is there likely to be an error that's occurred? Is there a correction that we need to make? that process then of reading out that information, doing the coding, and then making sure that we're able to correct our system as we go. Doing that in real time, I think, is a challenge across all kinds of codes. I think even the surface code, it remains an open problem. To actually get it at that pace of something like the order of microseconds, you would need to keep up with a superconducting processor in particular. But it's true that for LDPC codes, it's even more of an open problem. I think that a lot of work has been done in recent years about methods like what's called belief propagation, these different algorithms that you can use to try and solve this decoding problem for LDPC codes. But it really is a really interesting area. So we at Iceberg are looking more into that as well, at this problem of decoding, trying to find good approaches that solve that problem. But definitely it's one of the really exciting areas, I think, in this space, just like we talked about in the past. Maybe the logical gates were a barrier that people were working on overcoming. I think we'll see some really exciting progress in the next few years about this decoding in LDPC code.
And I guess, I mean, an area of exploration is sort of the integration, the tight integration of GPUs into these quantum devices, along the lines of quantum machines, OPX and DGX integration, right? But I mean, is it, my instinct says that ultimately, there'd need to be very customized silicon and maybe even a type of classical processor for decoding that we don't even have yet. Is that sort of a fair guess?
Yeah, it's really outside my expertise to talk about the classical hardware, but I think definitely that's my understanding too, is that we'll be dealing, when you really get to these devices, with really specialized hardware as well as software. So there's really multiple steps to the process, I think. There's the process of doing the theoretical work, developing these algorithms, and then absolutely there'll be an engineering challenge to really build out the whole software and hardware ecosystem that's going to be supporting that real-time device.
Which I think is not to say that GPUs won't be very relevant. I think it's right now. I mean, I think we need to throw everything we can at the problem, and I definitely think that something like GPUs have a lot of advantages, even on like the decoding side, because of how parallel they are. There are certain kinds of, decoding approaches for which it would be quite natural to use something like a GPU. So I think it's still a bit up in the air. Like there'll be a lot of different parts that go into this.
Yeah, I mean, you mentioned, Paul, sort of the hardware implementation being out of your scope of expertise, but you guys are working closely with a number of different hardware vendors at different modalities. Do you have a sense from them of what sort of level of acceleration or how does this unlock them? Does this compress their timelines in terms of getting to some kind of quantum advantage, or what does that look like for them, do you think?
Yeah, I mean, I definitely think that it would be wrong to say that we don't want to compress timelines, right? So I think approaches like this definitely do that. And if you look at their kind of roadmaps, I think certainly our hardware partners and other hardware companies as well all want to scale up to something like tens of thousands or hundreds of thousands of qubits kind of by the end of the decade, right? And so, there are still lots of challenges to get to that, but it's definitely, feels quite plausible that we will see some real progress this decade. And that, if a hardware company can kind of reach this 100,000 kind of number, hundreds of thousands of numbers, then, there's no obvious reason why, something, like a pinnacle architecture wouldn't have an obvious impact there.
And I'd just add to that as well. I think that it's important to emphasize that really at all levels of scaling, there's challenges to overcome with this hardware. So you might imagine, once you've got 1,000 qubits, can't you just make 1,000 times that and make 1,000,000? This is something I think John Martinez has written really well on, and he's working on this new company, that really there's different challenges at each level. And really, for example, this 100,000 to 1,000,000 qubit challenge, there's a whole bunch of questions in surface codes on superconducting qubits. For example, how do you manage needing multiple dilution refrigerators, networking these things together? At every level, new challenges emerge, and that's, I think, why these step changes of an order of magnitude here, an order of magnitude there, they could actually really translate to real-time line changes. It's not just a matter of taking a zero off your number.
Yeah. Well, and that's, there's the QLDPC work, but there's also algorithm optimization. You were leveraging work that Craig Gidney had done, but then you introduce some really clever algorithmic optimization as well. There's the reading from the single register because the reads are commutative, right? Or there was a trick with reading the data out of the register, a shared read, I think.
Yeah, I think this is a really good example of where it's important to have this hardware agnostic or broader approach. I mean, my guess, I wouldn't want to put words in his mouth, but my guess would be that this is something that Gidney in his work probably understood this is in principle a trick you could use. But in his framework of superconducting qubits that have this very fast runtime, it wasn't really relevant to this problem he was solving, which meant, I think, for that reason, he hadn't fleshed it out, he hadn't presented this work. But when you move to a different hardware platform like neutral atoms or trapped ions that might have a much slower cycle time, might have much longer runtimes, these kinds of approaches make a huge difference because this problem, how can you parallelize this if you've got a hardware platform where every operation takes 1,000 times as long on this platform as it does on superconducting qubits? Now it's not just a matter of how many qubits do I need, it's very much how do I make sure this thing is going to run in a week and not 50 years. And that really is the important thing there, is it's a way to be able to really scale, kind of trade off the number of qubits against time to recognize, okay, I need to bring this runtime below a target, a month, a week, something realistic. I need some lever I can pull to make that trade-off in a way that's compatible with my hardware. So that was really the focus there, was on thinking, okay, this works fine in that superconducting regime. When we look at a broader range of regimes like we do in the paper, how do we solve these problems? We weren't prepared to present results saying you can do this with 100,000 qubits, but it will take 100 years, because that wouldn't be, I don't think it'd be honest, I don't think it'd be interesting to anyone who wants those details. But absolutely, that was really the algorithmic side. So I don't see it so much as, it's not a huge step in the algorithmic direction. I think that this, as I say, is something that experts in that area, kind of a natural step forward. I see it more as an example of why it's so important to have this broader perspective, to not be too dependent on the assumptions of one hardware platform. And I think when you have obviously so many experts at a company like Google doing such great work, it's easy for everyone else to sort of just depend on their work without necessarily knowing the opportunities or challenges that might come up in different contexts.
Yeah. And I think there's a lesson there in we now have something like 100 different quantum hardware companies. That diversity is a resource we can leverage to try to come up with, as many different creative ways to, as you said, every level of this has serious problems and challenges that are not, so the science is not solved. It's not merely engineering. They're fundamental questions. So I feel like creative, open-mindedness and broad sort of horizons of thinking are really critical. I noticed also, not only, you've got sort of Scott Aronson weighing in on his blog saying it's serious work, and he's impressed by it. He has the same sort of caveats about there being a lot of engineering to be done, but you also acknowledged him in the paper for thoughtful feedback on the title of the paper. Can I ask what the original title was going to be?
Yeah, originally it was going to be, I think, how to break RSA with 100,000 qubits. And I suppose the concern was, out in the public, that might look like we've already done it, which we certainly have not. No one needs to be too worried right now. And so, that was the change, switch it to how we could reducing the overhead.
We wanted to acknowledge Scott because we did appreciate a lot. Obviously, he's had a whole lot of experience of how every in the quantum error can be misunderstood.
Yes,
had that experience. Obviously, it took him a moment to see. I know what people are going to think of this, right. And that experience was something we appreciated.
Yeah, he's been right out on the knife's edge of how the internet reacts to research topics and papers. So a good person to draw on, a good resource. So what's next for Iceberg and for the Pinnacle approach? What's sort of the next big milestones you're hoping to accomplish in the next 12 months?
Yeah, there's just like a lot in the pipeline. In general, we're expanding. So we just put out Pinnacle, and at the same time kind of announced our fundraise. And so we're just growing in general. We're opening an office in Berlin. We're growing our presence in the US, and we're bringing in like great people, which is exciting because great people do
Can I
great
just
work.
ask, those new offices, is that more about tapping into specific talent you want to add to the team, or is it more like market presence with hardware vendors that you want to partner with?
Yeah, more so the former. I mean, we've kind of, I think, almost saturated all the good people in Sydney. And so we just need to like go global. There's a lot of great people, obviously, in Europe and in the US. And I mean, they'll come on board, and then, over the next year, I think we just want to like keep on kind of improving the numbers. Like, I think Pinnacle's not kind of the end of the story. There's no
Have
obvious.
you got another order of magnitude in you?
Look, just from where we're sitting, there's no obvious flaw to where the numbers can get to. And I think, especially for such sensitive things like breaking RSA, it would probably be a big mistake to assume that the numbers are not going to keep going down.
That's really cool. Well, thank you so much for your time. It's a fascinating topic. It's really, I agree, it's very important work. And anytime you can lower something by an order of magnitude, given all the challenges, it is notable, important, and appreciated. So thank you very much, guys.
Thanks, Webster.
Yeah, thanks for having us.
Thanks again to Paul and Larry from Iceberg Quantum for such a great conversation. I'm really interested in what they're doing. I find quantum error correction in general as a topic really, really interesting. I hope you do too. This episode, again, brought to you by qubitsok.com, the signal in the noise for your quantum job search. Learn more at qubitsok.com. If you want to go deeper on the topics we cover, research highlights, commentary, and the occasional behind-the-scenes look at what's coming up for the show, sign up for the newsletter at newquantumera.com. It's free, and it's the best way to stay in the loop. And if you have an idea for a guest, a topic you'd like us to dig into, or just want to say hello, reach out through the website. I read everything. If you're enjoying the show, please subscribe wherever you listen to podcasts and leave a rating or review. It genuinely helps new listeners find us. And if you know someone who's quantum curious, send them an episode. Word of mouth is still how most people discover the podcast. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.